So this expression involving torque that says the sum of all external torque is rotational inertia times angular acceleration is a pretty powerful expression and applies to several situations. So here's another one that falls under the category of rotation of rigid bodies. So I just want you to imagine you've got a wall and then some sort of hinge that sticks out off of the wall. And then from that hinge, a strut, or we'll just call it a beam, sticks out of here like this. So there's the axis of rotation, and maybe a piece of string or something like this is holding this up, but then somebody takes their scissors and cuts the string, and all of a sudden this thing falls. Well, it doesn't, of course, the whole thing does not fall and translate downward. It's going to rotate in a clockwise direction about this axis. So the question goes something like this. What's the angular acceleration of the system? And what's the linear acceleration? Now, this is a tricky question because not all parts of the beam will have the same linear acceleration. The tip of the beam will accelerate more, and parts of the beam back toward the axis will accelerate less. And in fact, the portion of the beam here has no linear acceleration at all. It basically stays in place as the whole beam rotates. So every portion of the disk shares the same angular acceleration, but they all would have a different value of linear acceleration. So there's a concept that hasn't been identified yet that's important in rotation of rigid bodies that goes something like this. If I were to draw a vector diagram, and from now on, I think we're going to make what we call rigid body diagrams to replace what we've done in the past in the form of a free body diagram. Meaning, I'm not just going to replace this beam with a dot and say that there's a downward pull of gravity as the one and only force. Instead, I'm going to draw a diagram that allows me to illustrate lever arms if any lever arm should be identified. So I draw a dot for my axis of rotation, and then I draw an object with the same length as the beam, or that has the same dimensions as the object in question. And then I show the forces where they're applied. Now, let's be clear about this one. The problem says that we've cut the string. So there is no tension vector because the string is cut and it's gone. Okay, so there are a few forces involved here. There's a pull of gravity, and this is what I was talking about when I said there's a concept that hasn't been stated or illustrated yet. Where do we put the gravity vector? Where should the force vector that represents mg be located? Well, in truth, gravity pulls at all points of the beam. So there's a little bit of mass, dm, being pulled on by the Earth's gravitational field. And then there's also that little bit of mass times g. And every part of it is pulled on by gravity. But the net effect of all that, if I want to sum up all of the g times dm, that gives me one single force vector, mg, right? Because g would come out of the integral sign, and when I integrate dm, that just gives me all the mass. So where is that located? Mathematically, it acts as if all of the force of gravity that really is applying bit by bit everywhere across the beam, it's as if all of the gravity acts at the center of mass of the object. So that's another reason why you've gone through the exercise of trying to figure out how you can determine where the center of mass of an object is. It doesn't just apply in our study of collisions, it also applies in our study of rotation of rigid bodies. So there we have it. There's a force of mg. Now, whenever we see a force on a rigid body diagram, we try to identify if there's an associated lever arm. And of course, in this case, there is, right? That force has a lever arm measured from the axis of rotation to the point where that force is applied. And there's an angle between the lever arm and the force, and we've seen a lot of this, right? This won't always be the case, but we've got another example of an angle of 90 degrees. Okay, well, there are some other forces that are acting on this beam. Maybe just one other force. The hinge itself pushes against this end of the beam, but whatever force is in the hinge acts at the hinge. And so I can't associate or identify any lever arm that goes along with that force, so then I don't have to worry about it. Whatever force is acting at the hinge is non-torque producing. So there's really only one torque producing force, and it's due to the force of gravity. So our net torque is equal to the force of gravity in magnitude multiplied by the lever arm that we've identified multiplied by the sine of 90 degrees. Or in other words, our torque is equal to mg. Let's see, what's the lever arm we identified? If the whole beam has a length of L, then it looks like we have a lever arm equal to half of the length. The other half of the length of our beam extends beyond the center of mass. So mg is our force, L over 2 is our lever arm, and the sine of 90 degrees is just equal to 1. So we have a torque of mgl over 2. Where do we go from here? Torque, or I should say the net amount of torque, can always be substituted with I alpha. So the rotational inertia of our beam multiplied by its angular acceleration is equal to mgl over 2. Now, what is the rotational inertia of a beam? It depends on where the beam is rotated about. When a beam is rotated about its center, then its rotational inertia is 1/12 ml squared. But when a beam is rotated about its endpoint, you can find this, by the way, using the parallel axis theorem. If you've never used the parallel axis theorem to identify how the rotational inertia changes when the axis is moved from its center to some other point, I recommend you review some of my previous videos and give yourself a refresher on that one. Some of you know then that I is increased and becomes 1/3 ml squared when the axis of rotation is shifted to the endpoint. So that's the substitution we make, right? This is definitely a beam that's rotating about an axis through its end. 1/3 ml squared times alpha is equal to mgl divided by 2. We can cancel out the m. Can't entirely cancel out length, but we can get rid of one of the powers of length. So multiply both sides of the equation by 2, and we have 2/3 L times alpha is equal to G. So alpha is equal to 3/2 G over L. Okay. What point of the beam is rotating at that number of radians per second Well, it's kind of a silly question because the answer is all points rotate at that value, at least initially. That chunk of mass has an initial angular speed of 0 because the whole beam started out at rest, and that little chunk of mass has an initial angular speed of 0, and that bit of mass has an initial angular speed of 0. And when released from rest, every part of the beam all starts to rotate together, and by the time the beam has traveled a little bit, the whole beam then has gained some angular speed by the time it gets to this point, and so every point of the beam has the same value of alpha. But the reason I point out that this is just the initial angular speed is because that was all based on the force of gravity pulling at the center of mass with a lever arm of L over 2 and an angle of 90 degrees. Now notice when the beam is in the second orientation, the lever arm hasn't changed. The distance from the hinge to the center of mass is still a distance of L over 2, and the force of gravity still pulls straight down and still has a magnitude of mg. But you see what changed, don't you? The angle is no longer 90 degrees. The angle is now greater than 90 degrees. So because of that, the torque went from being equal to mg times L over 2. I'm tempted to write times sine of 90 degrees, but we know that's just 1. That's our initial torque. But when the beam reaches position number 2, the torque becomes mg L over 2 sine of theta, where theta is most definitely not equal to 90 degrees. And so the torque has decreased. You have the maximum amount of torque when it's in its initial position. And by the way, once the beam has gone completely vertical, well then what? Now how much torque is acting on it at this instant? I would say that there's still a force of gravity that acts at the center of mass. And I would say there's still a lever arm from the axis to the center of mass of L over 2. But now the angle between those two is equal to 0 degrees, and the sine of 0 itself is equal to 0. And so the torque, when the beam gets into position not 1, not 2, but 3 and goes vertical, the torque is now equal to 0. So you know, if there's a varying torque, then that leads to a varying value of alpha. And by the way, it's only if alpha is constant or uniform that you can use equations like omega squared equals omega naught squared plus 2 alpha theta, etc. In other words, rotational kinematics equations. But see, this is a case where our alpha is not constant because the torque varies. And so we cannot apply kinematics equations to the problem of the falling beam. But that's okay. We didn't set out to try to figure out what's the final velocity of the beam when it reaches the bottom. We were just asked, what's the angular acceleration of the beam? And I think we were also asked one more question when we set this one up. I don't recall where I wrote it down, but oh, here it is. We wanted to know not only the angular acceleration, but we also wanted to know the linear acceleration. So that's right. All parts of the beam have a common value for alpha that starts out being equal to 3/2 g over L. But as time goes on, even though all parts of the beam at any given instant in time, that part of the beam's value of alpha is the same as this portion of the beam's value of alpha is the same as this portion of the beam's alpha. All of those alphas are less than the initial alpha that every part of the beam had. Okay. But to make this even more challenging, all those parts of the beam do not have the same value for A, for a simple reason. Just as S is equal to theta r and V is equal to omega r, linear acceleration is equal to angular acceleration times r. So that means a point on the tip of this beam when it falls has a larger tangential acceleration than some point over here. And in fact, the point of the beam right next to the axis of rotation has a tangential acceleration of 0 because that portion of the beam stays in place. So there are actually parts of the beam. I'm going to draw a line and make a guess and say everything beyond that point has a tangential acceleration that's actually greater than free fall acceleration. And all the points in here, starting with this one that has an acceleration of 0, all the points on this portion of the beam have a tangential acceleration less than free fall acceleration. If that's the case, what exactly is this distance down the beam? Well, this should be easy if we just apply this relationship. So the tangential acceleration initially should be equal to whatever the associated value of lever arm is with the multiplied by the initial angular acceleration. So for example, if I want the initial linear acceleration for the tip of this beam, then I need to multiply that 3/2 g over L result that we got for alpha times whatever the distance is from the axis of rotation to the tip. But that would just be L. So I'm multiplying 3/2 g over L times L, and I find that the initial acceleration for the tip of this beam is equal to 3/2 of g, or 150% free fall acceleration. So, what's the location for a point that has an acceleration exactly equal to g? In other words, if alpha times r has to equal g, then what's r? R would be g over alpha. So if I take g and divide it by 3/2 g over L, g cancels out, and this is the same thing as r equals 2/3 L. So in my drawing, I think I made a pretty good guess. I sort of eyeballed it and estimated that points beyond that have accelerations that range from g up to the very tip, 1.5 g, and then for points within this guessed line, acceleration varies from 0 up to g. And so what is this distance right here? It's 2/3 of L, and this is the remaining 1/3. So the way this would work, if you have a way of setting up something like this, give it a shot. Find a way of hinging a straight beam at its end and then drop it. And what I'd like you to do is place a few paper clips or pennies or some little objects all along the length of it. And then get out your cell phone or your iPhone and take a video in slow mode and release from rest and watch what happens. You'll see, if you can advance frame by frame in your playback of the video, that the pennies are remain stuck to the beam up to about this distance, which would be 2/3 the length. And the pennies beyond there aren't in contact. They've separated away from the end of the beam, meaning that this portion of the beam is falling greater than free fall, which would describe the motion of the pennies or the paper clips. So just an experiment that you might want to try on your own to verify the equations that express both the angular acceleration and the linear acceleration of the points of a beam.